Welcome to Engineering Dynamics. I'm your host, Dr. Walk, and today we're going to be going over how to represent vectors in different coordinate systems. So the first coordinate system that I want to start out with is going to be the Cartesian coordinate system. The Cartesian coordinate system inherently is also an inertial reference frame. So an inertial reference frame means that it's fixed to the Earth. It is allowed to rotate, but it cannot accelerate. It can translate with constant velocity. So that's an inertial reference frame. It's important to understand the difference between an inertial reference frame and rotating reference frames. And you're going to see why throughout this lecture, but just keep in mind the first coordinate system that we're going to represent our vectors in is going to be an inertial reference frame, which we happen to call Cartesian or rectangular coordinate system. So let's go ahead and draw out what you're most familiar with, and this is going to be the Cartesian. So we have our axes, and then we have our unit vectors. And unit vectors they're just direction vectors, right? They just define what direction our motion is occurring in. And in the Cartesian coordinate system, we have unit vectors that are labeled I, J, and K. So if I wanted to say, okay, let's find a random point P, and let's go ahead and define a position vector to point P. So I'm still getting used to this pad, sorry guys. All right, so this is going to be our position vector to point P, and we're going to do it in relation to the inertial reference frame. So a lot of professors will use a notation where this subscript is going to be the letter of whatever it's pointing to. So I called this particle P. So I said that this was P. And so my vector is going to have a subscript P, and it is going to come from the inertial reference frame. So if I just label this an origin O, I can, my colors aren't doing good. There we go. We can have O. Okay. So now I can say, all right, well, how do I represent that? That's graphically, right? Like, how do I say, like, what does that actually look like mathematically? So this is the position vector to P in relation to the Cartesian coordinate system or the inertial coordinate system. And what that's going to look like if we say this is going to be in 3 dimensions. So I'm going to say this is like somewhere here and here. So it's going to be some distance in the x direction, or some distance along the x-axis in the I direction, plus some distance along the y-axis in the j direction, plus some distance along the z-axis in the k-hat direction. So this is our position vector. If I want to get velocity, velocity is simply the time derivative of your vector. If it's a time derivative, you can represent it by using a dot. Okay, so we're going to represent it like this just to cut down on notation. And if we take the derivative of this first parameter, we see that x, that's going to be a variable, but is I a variable or a constant? It's going to be a constant because we said that this is an inertial reference frame, which means that these guys aren't moving. They will always stay in these directions. So the derivative is just going to be whatever the derivative of that x is, okay? And that's going to be in the I direction plus the derivative of y in the j direction plus the derivative of z in the k direction. We can do the same thing to get acceleration. Acceleration is going to be the derivative of your velocity vector in terms of time. This can be represented as a double dot vector. So this is the acceleration of point P in the inertial reference frame. which will equal x double dot. It's just going to be the derivative of velocity, which is acceleration in the I direction, plus acceleration in the j direction, plus acceleration in the k direction. That's it. So we successfully defined our our vectors in the Cartesian reference frame. So now we're going to take this and we are going to define, or I wonder if I can just move it over here. Let me see. Oh, I can. Okay. So now we're going to take this and we're going to say, can I take this point P and can I represent it in a different coordinate system? Why would I even want to do that? Well, sometimes motions are easier to analyze when using different unit vectors. The whole point of a unit vector is to understand the direction of motion. Well, not all motion occurs in this linear way. So when we analyze motion that is linear or a projectile, we are going to use Cartesian or an inertial reference frame. But what happens when the particle or the rigid body is not moving in a linear fashion? It's moving more in a curvilinear way. Well, then we can choose between two different rotating reference frames. The first rotating reference frame that we can choose from is, let's do normal and tangential. So we have normal and tangential. So what I can say is, if this path or if this point is following a known path that kind of goes this way, I can say, well, I know that path, and I know that it's going to have a unit vector here, and it'll have a unit vector here, and this unit vector is going to be tangential to the curve and in the direction of motion. So if my particle is moving like this, my tangential unit vector is going to represent that. Then I'm going to have an EN, a unit vector in the normal direction. And the normal direction is interesting. This can flip. It can go this way or this way depending on the curve. So let's take this over here so my drawing doesn't get too crazy. If I have something like this, this is my path. Now remember, when using this coordinate system, you have to know the path. It has to be given. Say the particle is here, and then it moves here, and then it moves here, and then it keeps moving along this curve. Well, my tangential unit vector, my ET, is always going to be tangential to the curve and in the direction of motion. So that's not going to change, okay? And then we'll do one last one here for good measure. Okay, but now my unit vector in the normal direction, it can change. It can flip. So here it's going to be pointing this way. That's EN. But here it's going to be pointing this way, and then this way, and then this way. Do you guys know why it flips every time? Well, it's going to flip because it's always pointing in the direction of curvature. So at every point, your particle, right, it's going to be on a path that has its own circle. Okay, so here you see how the path curves differently. It has a circle here, and it has a circle here, and it has a circle here. So your normal unit vector is always going to be pointing directly into that circle. And another interesting parameter that we have in this coordinate system is that the center of its unique circle to the particle itself, that distance there, that distance is known as the distance of curvature, and we denote it by rho. Denote it by rho. Okay? So this becomes a little bit more difficult, I think, for some students to visualize. So let's go back to our whole goal is to represent a position vector in different coordinate systems. So we have a position vector here in the Cartesian coordinate system, and now I am going to represent my position vector of P in my normal and tangential coordinate system. Now I'm going to represent it in this frame. So my R here, I have to represent what does that look like from this frame here. Well, honestly, like I said, to use this path, or to use this coordinate system, this reference frame, your path has to be known. Has to be. All I can tell you is that the path is going to be, has to be in terms of S, because S is the position along the path, and time, because this here can be at this position originally, but then maybe it can be here in the second position. Oh, let's make that green. Okay, so this could be like P2, and then we're going to have our P sub 2. Oh dear. How do I go back? Well, there we go. So here we have our P sub 2 in the O frame. So here I'm going to say, okay, well, this position vector is going to be dependent on wherever it is along this curve, which we denoted the distance along this curve as variable s at a certain time. So all I can tell you is that this R is going to be in terms of S and T. I don't know what it is, I don't know what it looks like, but you guys are going to be given that, okay, because that is a requirement to use this frame. But what we could do is derive what its velocity of P and NT looks like, because what is the kinematic relation of velocity? Well, velocity is just the derivative of position. So we have dr dt. And if we look here, we have an R, we have a T, and we have a T. What we're missing is an S. So we could just multiply the top and bottom by ds. Okay, so what does ds dt equal? ds dt is going to be the velocity of the point along this curve. So really that's going to be velocity. And then we're left with this dr ds business. What does that mean? Well, let's take a look at these vectors again. If this is rp1 and then this sometime later is rp2, and it's going to have a path right there, this is going to be S1 and S2. So this is going to be the change in S. So we can say it's going to be like a little small increment of S, and this is going to be a really small increment of dr. Well, if you take infinitely small, this curve eventually becomes a straight line because they're so close together. Well, our definition of this straight line, because it's in the direction of motion and it's from one position to the next, it really is the definition of your unit vector in the tangential direction. Because if you look here at every little teeny spot, this little line, this unit, is going to be represented by this line. So we can say that dr ds is really equal to the unit vector in the tangential direction. This is important because this statement states that the velocity is only in the tangential direction only. So you're not going to have velocity in the normal direction, only in the tangential. Alright, so that's our position vector and our velocity vector in the normal tangential. What about the acceleration? What about the acceleration of p in the normal and the tangential? Well, I have to take the derivative of this. So this is going to equal the time derivative of v et. Velocity is going to be a variable. Now, is the unit vector et a constant or a variable? It's going to be a variable. It's going to be a variable because now our coordinate system is no longer inertial. Our inertial frame, that's fixed, but we put this frame on the particle, so it's stuck to the particle. So everywhere the particle goes, it's going to go, which means as it rotates down, I can say that this is ET is going to change to this direction, and EN is here, and it's going to keep changing. You can kind of see it more better here. So you can see that this T, it goes along here, and it changes kind of directions. It's not steady, like it's not fixed like Y and X are. It can change with the particle. So let's go ahead and take a look here. If this is a variable and this is a variable, when you take a derivative of two variables, what rule are you going to have to use? You're going to have to use the product rule, which is going to state I'm going to take the derivative of the first, which is going to be v dot, or we can just call it, let's go back here. We can say that the derivative of velocity is acceleration, and then we have to say plus the first times the derivative of the second. Okay, but do you know what the derivative of a unit vector is? Well, this is going to be kind of hard. So we have to relate it back to something that we know. So if I go up here, what I want to say is I want to relate it back to the Cartesian coordinate systems, because I can take derivatives of these vectors, and you'll see why in just a second. So if I take my X and Y frame, these don't move, right? At any time, my normal and my tangential unit vectors are going to be some angle away from them, right? If they were aligned directly, then it's theta 0. But as my normal and tangential reference frame rotates, it's always going to be some degree from the x-axis, right? So I can say that ET is equal to, now this is a unit vector, and what I'm going to do is I'm just going to express ET in the inertial reference frame. So if I express it in the inertial reference frame, I have to project this unit vector onto the x-axis and this unit vector onto the y-axis. So I'm going to break it up into components essentially. So I'm going to say the magnitude of this is just 1. So I'm going to have 1 cosine theta in the I direction plus 1 sine theta in the j direction. Okay, but I'm interested in the derivative. So I'm going to take the derivative in terms of time. So the derivative in terms of time, the derivative of cosine is going to be negative sine theta, but we're doing it in terms of time, so we have to pull out that theta dot. So this is going to be theta dot I plus the derivative of sine is cosine, theta. Again, we're doing it in terms of time, so we have to pull out that. I think you guys call it U substitution, right? So that doesn't help me though, because let's go a step further and you'll see it kind of all connect together here. So if I say that's going to be representing the ET unit vector in the inertial frame, let's go ahead and represent the EN in the inertial reference frame. And we're going to get, so we take this unit vector and we are going to break it up into components or project it onto the axes in the inertial reference frame. So here we have negative sine theta I plus cosine theta j. Now pause here and look at what we have. If you look here, we have negative sine theta in the I direction plus cosine theta in the j direction. En is negative theta in the I direction and cosine theta in the j direction. So really, the derivative of ET in terms of time is going to equal, and we can, this will now be expressed in the ET, this is going to equal theta dot, because don't forget that you have to include your theta dot, times En. You see that? So really, and if you don't believe me, all we have to say is, okay, well, theta dot times En. En is negative sine theta I plus cosine theta j. If I factor these in, I get negative theta dot sine theta I plus theta dot cosine theta j. And that's what I have up here. Okay? So by doing that, it makes taking derivatives of unit vectors possible. So I'm going to go ahead and take my acceleration. I'm just going to put it down here. I had r double dot in the normal and the tangential. So I have an acceleration of point P in the normal and tangential is going to equal my linear acceleration. So my linear acceleration in the tangential direction plus velocity, which is here, and then you multiply it by the derivative of your unit vector, which we found, and that's going to be theta dot En. Now, this is a great answer. This is fine, but remember we said what was unique to this reference frame? We had this parameter called rho. Okay, so if we look at the relationship here of what does theta and rho and all that stuff have in common, well, let's look at our vectors again. This is RP1 and RP2. This is going to be theta. This is S, okay? And this, we already said that in the circle, it would be called rho. We can say that S is equal to rho theta. S is equal to rho theta. Now, stick with me. I could also say that the derivative of S in terms of time is equal to rho, because rho is a constant, so it's just going to stay rho, is equal to d theta dt. Okay, well, let's take this here and let's copy it down here so we can see what we're working with. We said that we had ds dt is equal to rho d theta dt. Well, d theta dt is the time derivative of your angular position, and your time derivative of your angular position is denoted theta dot. So this is interesting because I have a theta dot here. So if I solve for theta dot in this equation, I have that theta dot is equal to, I'm going to move rho over, 1 over rho ds dt. And we said earlier that ds dt is really the velocity of the particle moving along the path. So this ds dt is velocity. So theta dot is equal to velocity over rho. Now I can plug that back into here, so I can put this in here. And I have two v's, so I can say that the acceleration of point P in the normal and the tangential reference frame is equal to the linear acceleration in the tangential direction plus velocity squared divided by rho in the normal direction. And that's it. So now you have position, velocity, and acceleration both represented in the inertial frame, which is commonly known as Cartesian reference frame, and you have the position of point P, that same point, represented in the normal and the tangential direction. So now there's one more coordinate system that I want to introduce, the third reference frame. Third reference frame, we're going to still have this point P, but now I'm going to say, you know, the motion of the particle has changed a little bit. It's no longer following a known path. I have no idea what the path is. So I'm going to redraw this just to kind of clear things up a little bit. Okay, you still have your x, your y, and your z, and you still have your point P, and you still have your position vector locating P. Okay, so but this time I'm going to say, you know what, I really don't know what this point is doing. I do know that it is moving along in some kind of curvilinear way, because if it wasn't in curvilinear, I would just keep it in the inertial reference frame. So I know it's moving, and I also kind of see that it might be moving in and out, which is interesting. But I don't know the path. I really don't know anything much more. So what I'm going to say is, well, I'm going to define a vector, and I'm going to define it as ER and E theta. Okay, and the reason I'm going to do this because this particle is, I don't know the path, like I said, but I do know that it's moving somewhere in this direction, and it's also rotating. So a really good example, this is one of my favorite examples, so thanks to my son. So you have a fire truck, and I'm going to put the inertial reference frame right here. Okay, so your y and your x. Let's move to 2 dimensions for now. So this is y and x, and then I'm going to have right here, I have a little eraser. I don't know if you guys can see that. I put an eraser on there, and that's going to be your point P. And I attached a ER going this way and an E theta going this way. So ER represents the motion direction that this ladder would take if it extended. Okay, so when it's extending or it's collapsing backward, that motion vector ER really defines it well, because remember, unit vectors are always in the direction of motion. So if I have a motion that kind of goes in and out, right, then it's really best described using that ER unit vector. This ladder also allows me to rotate. Okay, so again, this motion, I can put an ER this way and an E theta going this way. So E theta, if I take 2 pens and I say that this is, red pen is E theta and the green pen is ER, I can see that as I extend, right, it goes in the path of the green vector, but as I rotate, it's going to go in the path of the red. Okay, so having different coordinate systems, it might seem like overkill when you're learning, but it makes problems so much easier to solve if the vectors are already in the direction of motion. And this is because we don't have to break them up into components. Say if I had this dot was going in and out, every time I analyze its location, I wanted to use your normal Cartesian, I would have to break that up into components every single time. So I'm going to have several cosines and sines everywhere. But if I learn to use this reference frame we're going to call polar. And in polar, you have radial and transverse coordinate unit vectors. Okay, so you have radial and transverse coordinate vectors. Now, we have to go back to our main goal. We said that we wanted to represent the position of point P in the, it's going to be the polar coordinate frame, but we'll just say the radial and transverse reference frame, okay? So how do I do that? Well, I know that it's going to be just like I did up at the Cartesian coordinates. I said that, well, I have to break this up into components, this r, and it's going to be some distance along the x, some distance along the y, and some distance along the z. Well, now my unit vectors aren't in I, j, and k. My unit vector is in r. So now I'm going to just simply have some magnitude in the r direction, er. And that's it. That's all my position is. I don't have to define anything in this direction because the particle is lying on this axis. Okay, so that would be like if I had a particle here and I said that r is equal to some distance in the j direction. It's not in the x or the z. Okay, so I can just put 1. This particle lies on this axis, so it's simply some magnitude r in the er direction. Now, when I take velocity, which is the derivative position in terms of time, in the radial and transverse coordinate frame, I have to look at these. This is 2 parameters, right, or 2 variables in 1 parameter. I have r. R can change because my ladder can go in and out, and er can change direction because my ladder can rotate, okay? So at one point, er might be here, but at the second location, er is now going to be pointing a different direction, okay? So these 2 are going to be variables. That means I have to use the product rule. If I do the derivative of the first times second plus first times derivative of the second, I get this. Now, note that r dot is velocity, okay? So you have velocity there. But I need to say, okay, well, what is er dt? And we learned one way up here of how to do that, and we really just used the projection. There's another way you can do it. You can use a cross product. If you are going to be going into like space mechanics or robotic arms or something like that, a lot of times what they do is they use a cross product. So they'll use v equals omega cross r. I think for this video, because I don't want to confuse anyone, I'm going to stick with the method that we already used, and then I'll go back and I will show you that they're the same thing. Okay? So let's find out what is the derivative of the unit vector in the radial direction. What's the derivative of that? So first I have to start with my inertial reference frame, which is x and y, and in between x and y is going to be, so if I put my point, take my axes up here and I have x, and I have y. You see that ER is between x and y. So the unit vector I'm going to draw on this side is ER. And this side is going to be E theta. And I can extend my negative x-axis out if I wanted. And then I'm going to say, okay, well, what is the angle between here and here? And that in polar form, if I were to project this down, this would be, somewhere around here. And in polar, in 2 dimensions, we always say that it's theta. So theta is between the unit vector, and then if I take my unit vectors down here and I project them here, this is ER and this is E theta. Okay, so here we can say that the angle between the x-axis and the ER is going to be theta. So that's where I know to put theta. Okay. As you get into more advanced classes, I want you to not assume that it's theta always between x and y. Sometimes theta will go between, starting from the y-axis. You really have to analyze the mechanism that you're looking at. All right, so let's go ahead and define what ER is. ER is going to equal, again, I'm just projecting downward, so this is going to be cosine theta I plus sine theta j. And the derivative of this unit vector in terms of time is going to be negative theta dot sine theta I plus theta dot cosine theta j. And E theta is going to equal negative sine theta I plus cosine theta j. So I can express this one. So you see how this is negative sine theta I. I have a negative sine theta I here. And I have a positive cosine j there. So I can really say that the derivative of the unit vector in the radial direction is going to be equal to theta dot E theta. So my position, the velocity of my point P in terms of my radial and transverse coordinate system is going to equal r dot ER plus theta dot R E theta. Okay? And then you can do that, of course, to get acceleration. We can just do this again. So if I do the acceleration of point P in the polar coordinate system is going to equal, now I have to take the derivative here. This derivative will be a dot product. So I have to say the first times the second plus the, I'm going to do the first times the derivative of the second here in terms of time. That's going to be my first. Now here I have 3 variables, so I will have to do the dot product for each one. So I'm going to say the derivative of the first times the second and third plus, this is plus the second, so theta dot R dot E theta. And then I'm going to say plus the third term, so I'm going to say theta dot R derivative of E of my unit vector in terms of time. Now here I can go ahead, alright, so now I have to say, okay, well, let's go back and take that derivative. What is dE theta dt? Well, this is going to be negative theta dot cosine theta I minus theta dot sine theta j. So this is going to look a lot like this, except for this has a negative and a theta dot. So my dE theta dt would equal negative theta dot ER. So I can replace this with negative theta dot ER. So let's go ahead and clean this up. And we have that R double dot P equals, oh, and I have to replace this one here. So this one here we've already done, and it is theta dot E theta. So we have R double dot ER plus R dot E theta plus theta double dot R E theta plus theta dot R dot E theta. And these all have the little caret tops on it. And then plus our last term, which was theta dot R times negative theta dot ER. So let's go ahead and group like terms. So we have R double dot P, and again this is a acceleration vector expressed in the radial and transverse. Change that. This is going to be the radial and transverse. So let's go ahead and say ER, we have linear acceleration in the radial direction, and we also have this term here. This is going to be negative theta dot, there's two of them, squared R in the ER direction, plus now we have to group all of these ones. Okay, so we have, looks like we have two of these are the same terms. So this is going to be 2 R dot theta dot, and then we're going to say plus theta double dot R E theta. And I'm going to just rewrite this because this is not the conventional way to write it. We always write the higher terms first. So this term really should come first. It should be theta double dot R plus 2 R dot theta dot. So I'm going to just replace this because I want you guys to, you know, follow convention. So I mean, it's like when you do an equation with like x cubed plus x plus 3, you wouldn't put the 3 first, right? So just kind of stick with this. So you're going to say theta double dot R plus 2 R dot theta dot. And while we're here, let's make sure we understand what each term actually means. So this is the acceleration of point P expressed in the radial and the transverse direction. So this is going to be made up of a linear acceleration in the radial direction. It's also going to be made up of centripetal acceleration. So centripetal acceleration, you see the negative? If we have x and y, and we said P was out here, and we said that this was ER, and this was E theta. This is saying that it's going in, this is some acceleration in the negative ER direction. So it has to be, we labeled this as positive ER, this is negative ER. Just like if this was X, this is negative X. Okay, so this is going to be the negative ER direction. So this acceleration is going to be going inward. So that's what that looks like. And we call that the centripetal acceleration. So if you have the ball on a string and you spin it around and around and around, it's that acceleration that is being pulled inward. This acceleration is called the transverse acceleration, and this acceleration is known as the Coriolis acceleration. Coriolis acceleration is like an inertial acceleration. It's used as a correction factor in inertial reference frames. And if you want to think about it as like, what does that actually like mean? When you are in a car, like and you're standing in the back of a pickup truck, and the car suddenly goes forward, the acceleration is going forward. but your body feels like it's delayed. It's kind of like pulling backward. That feeling, that internal part, that is going to be the correction factor or the Coriolis acceleration. Okay, so in summary, we just derived position, velocity, acceleration of 1 point in 3 different reference frames. Okay, I'll see you in my next video.